Here's kind of a classic physics problem. We've got a car going around a banked corner. So if we look at the overhead view, the car is traveling around the circle in this direction. And in the front view, we've got the car moving towards us. And the question, we're given the coefficient of static. This is a coefficient of static friction between the tires and the road, and we're given the angle of the hill. And we are asked to find what speed could you go around that curve without any friction at all? What's the fastest the car could go around that curve, and what's the slowest the car could go around that curve? Now, I want to begin by saying that 0.316 is a very small coefficient of static friction for wheels on a road. Wheels typically have tires, good tires, typically have coefficients of friction between 0.9 and 1. But we're going to assume that this is either rainy or snowy or something that gives a low coefficient of friction. All right, so the questions were, what speed can the car go around without any friction? What's the maximum speed it can go around? And what's the minimum speed it can go around? All right, so let's start with part A. For part A, let's look at the forces that are acting on the car. So there is a normal force that points up from the ground, perpendicular to the ground. So that's going to point in this direction. And there's a gravitational force, which pulls straight down towards the center of the Earth. And normally there'd be a friction force, and the friction force would either point parallel to the hill this way or parallel to the hill that way. But we're told for part 1 that there's no friction, so we're just going to leave that off. And I'm going to label this one mg, that's the gravitational force. Okay, so we also know that the acceleration points towards the center of the circle, so ma points towards the center of the circle. All right, that gives us what we need to do part A. So we're going to create a coordinate system where let's create our coordinate system. We got 2 choices for the coordinate system. We can either create our coordinate system so that downhill is the x direction and perpendicular to the hill is the y direction, or we can create a coordinate system where horizontal is the x direction and vertical is the y direction. Either one works. I was trying to think which would be easier, but we'll just go with vertical and horizontal. And the reason I'm going with vertical and horizontal is because the acceleration is horizontal, and I'd like the acceleration to point in the x direction only. So if we add up all of the forces in the x direction, it should equal mass times the x component of the acceleration. And if we add up all the forces in the y direction, it should be mass times the y component of the acceleration. In the x direction, the normal force has both an x component and a y component, and this angle in here is theta, the same as the angle of the hill. So we get the opposite side is the x, so this is going to be normal force times sine theta is equal to ma. And in the y direction, we're going to get normal force cosine theta minus mg is equal to 0. So the normal force is going to be mg divided by cos theta, which we don't end up needing for this problem. What we do need is the x equation. I guess we do need the y. I guess we do need the y equation, because now I need to plug in normal force is mg divided by cos theta times sine theta equals ma. And now for a, I can plug in v squared over r because we are traveling in a circle. Okay, I guess I should have given the radius of the circle as one of the givens for the problem. So let's say that this is 50 meters. All right, let's see. My masses cancel, and sine divided by cosine is tangent. So this is g tan theta is equal to v squared over r. So v is equal to the square root of gr tan theta. So that is 9.81 times 50 times the tangent of 20 degrees. Sorry. Having a little bit of a challenge typing this into my calculator. Now I'm taking the square root of 9.81 times 50 times the tangent of 20 degrees, and I get 13.36 meters per second. And the problem has, well, let's make this 50.0 meters. That way the problem has 3 significant digits. So this would be, for part A, the answer would be 13.4 meters per second. Okay, so now let's redo the problem for part B. So part B says, what's the maximum speed? So let me okay. All right, let me just go ahead and delete all this. It's in the video. Or I guess I can just move it out of the way. And now we can do the problem when we're going as fast as possible. Now, if you go too fast, what happens? If you go too fast, the car slides outward, right? It doesn't make it around the corner. If you go too fast, you don't make it around the corner, and the car slides up the hill. So if we're going as fast as we possibly can, if there was no friction, we would slide up the hill. So that means that friction points down the hill. And if we're going as fast as we possibly can, then we're going to be using the maximum possible friction force. So that means that my friction force is going to equal mu sub s times the normal force. Okay, so let's, and this only happens when we're using the maximum possible static friction. Okay, so let's see what happens with this problem. So we are going to do this the same way. We're going to add up all the x components of all the forces and set that equal to mass times the x component of the acceleration. And we're going to add up all the y components of all the forces and set that equal to mass times the y component of the acceleration. So when we do that, tell you what, we could do it this way, and it would be fine. But I am going to switch my coordinate system so that the x direction points down the hill and the y direction points perpendicular to the hill. Now that's a little bit of a challenge because that means that both the gravity force, let's see what color will show up well, maybe green. The gravity force is going to have an angle theta here, and the acceleration is going to have an angle theta there. Okay, so that's a little bit tricky, but we'll make it work. All right, so when I add up all the forces in the x direction, I get the friction force is now completely in the x direction, and mg sine theta also points in the x direction, and that's equal to ma cosine theta, because the acceleration has a component that points in the x direction, but not the whole thing points in the x direction. Okay, and in the y direction, I have a normal force minus mg cos theta, because a component of cosine of gravity points in the negative y direction, is equal to ma sine theta. Okay, so this is going to allow me to solve for the normal force. The normal force is equal to ma sine theta plus mg cos theta. And the friction force is equal to mu s times the normal force. So the friction force is going to equal mu s ma sine theta plus mu s mg cosine theta. Okay, so let's take that and plug it in to the x equation. So we have mu s ma sine theta plus mu s mg cosine theta. That's my friction force, plus mg sine theta equals ma cosine theta. All right. Ultimately, we're going to be trying to solve for velocity, but to do that, we need to solve for the acceleration. So what I want to do is get everything with acceleration on one side of the equation and everything that doesn't have acceleration on the other side of the equation. So, so I see acceleration in this term and this term, so let's get those both on the right-hand side of the equation. So we're going to have ma cos theta. Oh, before we do that, we've got m in every term, so let's cancel the m's. Okay, so now we can do a cos theta minus mu s a sine theta equals mu s g cos theta plus g sine theta. All right, and then finally, well, not quite finally, these both have a in it, so I'm going to pull out the a, and that leaves us with cos theta minus mu s sine theta equals that. Well, okay, fine. Let's put that back up. For this one, let's pull out the g. So this is equal to g times mu s cos theta plus sine theta. So finally I can solve this for A. A is equal to G times mu s cos theta plus sine theta divided by cos theta minus mu s sine theta. And okay, so A is equal to v squared over r. So to find v, we're going to multiply both sides by r, and then we're going to take the square root. So v is equal to square root of gr times mu s cos theta plus sine theta divided by cos theta minus mu s sine theta. And I want to do two quick things before we plug in any numbers. The first one is, what if there was no friction? What if mu s was 0? If there was no friction, then that would be 0 and that would be 0, and sine divided by cosine would be tangent, and we'd get v is equal to gr tan theta, which is in fact what we got when we said there was no friction. Cool. Okay, what about if the angle was 0? If the angle was 0, then this sine theta and mu cosine and sine theta would be 0 if the angle was 0. And if the angle was 0, cosine theta would be 1. So we would end up with mu s times gr, which is what we got in the previous video. V is equal to mu s gr when we had a flat hill. So if the angle is 0, we get the answer that we got with no hill. And if the friction is 0, we get the answer that we got with no friction. And so this seems like a very reasonable equation. So let's see what we get for the velocity. G is 9.81, R is 50 meters, mu is 0.316, and theta is 20. Okay, so 0.316 times the cosine of 20 degrees plus the sine of 20 degrees divided by the cosine of 20 degrees minus 0.316 times the sine of 20 degrees. Okay, typed all that in, and I get 19.4132 meters per second. We're supposed to be using 3 significant digits, so that's 19.4 meters per second for part B. And if we compare that to part A, which was 13.4 meters per second, we see that you can go faster with friction than you can without friction, and that makes sense. The fastest you can go is faster than you could go with no friction. All right, well, what do we do when we want to go as slow as we can possibly go? Well, if we want to go as slow as we can possibly go, what happens is the friction force now points in the opposite direction. Because if you're going really slow, you're in danger of sliding down the hill. So friction's going to point uphill to make sure that you don't slide down the hill. Okay, so what's the slowest you can possibly go? The answer we're going to get is... The answer we're going to get, okay, what would happen is we would do this problem the exact same way, except this friction force would be negative because it would be pointing up the hill instead of down the hill, which means that both of these would be negative, okay? Which means that this would be negative and this would be positive, which means that this would be negative and this would be positive, which means that this would be negative and this would be positive, which means that this would be negative and this would be positive. So the problem ends up being all the algebra ends up being exactly the same, except we have some positives and negatives in different places, and now this is for part C. And so for part C, if we plug this in, we get adding in the negative sign in the numerator and changing the negative sign to a positive sign in the denominator, and we get the slowest you can go is 4.59 meters per second. If you're trying to go as slow as possible without sliding down the hill. And remember, this was on a very icy day where mu was a small number, so sliding down the hill is, if you're not driving at all, if you're just sitting on this hill, you slide down the hill because friction's not enough to keep you going, to keep you on the hill. You actually have to be driving to avoid sliding down the hill. Okay, that was a long problem. Had some good things in there that might help you with some of your homework.